So here we are again, once more, recording another video for our series on Turing Complete. And the level we are going to play is signed less. Hope it's getting late. It's getting quite late. Maybe you can see the time. It's close to, what is it? 11 p.m. And I'm a little bit tired. Create a circuit that outputs when the first input is less than the second. Interprets the byte as being signed. Interpret the byte as being signed. Alright, we are going to do signed less. And yeah, it's going to be very similar solution to unsigned less. So maybe we can let us delete this. I don't need it anymore. We can maybe copy this so that we can actually copy and import. Nice. But this time there's going to be a difference, because now the least or the most significant bit is the minus 128, and what exactly does it mean for our circuits? Let's think about that for a second. Okay. Let's see. How does it look like? Again, let's negate the number. This is minus 123. So there's a case where the first number is negative and the second number is not. In this case, this number is lower. Also, I guess this part has to go. Like, this takes care of the positive part of the number, right? I'm actually having trouble focusing right now. Oh, I should have instantly recorded the video. So now I'm totally out. Maybe we can also use this component. Well, we could determine where the first byte differs, the first bit differs. Instead of building this. We could have done this in Signless as well. Anyway, we didn't. We've built it like this, and this is great. Since it inverts the whole thing, things become difficult. It should be -5, right? No, it's -6. It's not even inverted, it is inverted +1. Maybe we could negate one of the numbers and then use this circuit. Does this work? No, it does not. Maybe if we negate the first one. Does this make a difference? No. Because we would negate only so the first thing we would do is we would determine, this feels so strange, if there's a difference in these two. If there's a difference in these two, we would have to go a special route. If there's a difference in these two, if there's no difference in these two, we go this route, right? which would mean that in theory we could delete this. This makes it actually more difficult, so let's leave it like it is. So if there's a difference in these two, we would be able to determine which one is lower just by knowing this. The question is the first number lower? So if this one there's a difference in these two and this one is lining up, we would have true. So what do we do in case there's no difference? We then just let's see if we even have to think about this, because in theory we could just try this, see if it works. No, not like this, the other way around. No, actually this way around. You go here and you go here. No, it does not work. Oh, it would work. So first of all, you can never be true. So it's minus one less. So in case you are true, there is a difference. So there actually has to be a XOR. Or rather an AND, maybe an AND is because if you are not true, if there's no difference, if there is a difference, in the least significant bits. Does this change anything? Yes, it does. So what does it do? It works if one number is negative and the other is not. And it works for negative numbers as well. And if we have positive numbers, okay, there's no difference in these two. So you don't go there. It's only if there's a difference. When this circuit gets deactivated. No, because you do not belong here, you belong here. That actually solved the level. Great. Got a little bit confused on that one, but we made it. I feel like I didn't explain it well. Okay, so let's try this one more time. Okay, the logic is basically the same as in the last level, right? Interestingly enough, we don't negate. Because apparently in case of negative numbers, it's still the most significant bit that decides whether a number is higher or lower. Okay, so if there's a difference in the most significant bit, which is the sign bit, right? We would first of all deactivate this circuit. By fitting a knot in the end. And then we would just go yes or no. Oh wait, if there's no difference in the most significant bit, we would then feed a yes signal into the AND and open it up. If there is a difference, we then close off this part of the circuit and just determine from just these two, is it higher or lower? Because in case the first number has an active and the second does not, if there's a difference and it is active in the first one, we would have a yes, and the other scenario would give us a no, since this condition wouldn't be met, and so this AND wouldn't be giving us a positive signal, so positive out. Okay, so if there's no difference, then thanks to this NOT, we would open up this AND gate for this circuit to determine which number is lower. So in case of negative numbers, let's go like this. Let's maybe go like this. It's gonna be easier. So 15 is higher than 13. Was 115 is higher. Well, because the number that has more active bits is the lower one. Which is not the case. So if this number is lower, I feel like we should use a MUX. Because in theory, when this part of the circuit, like these should be the same, right? These should give us the same output. Minus 13 is not lower than 15. $115 is not lower than 113. Yes, because the number that has more active bits is the higher number in both cases. Interesting. Okay, I hope this made sense. I just explained it to myself. Here we are. Hope you could follow me. Maybe you were faster than me, which would be great. If not, it's not a problem, I guess. If you didn't manage to follow this logic, maybe think it through. So, I don't know, we already know this component, so we discussed it on the last level. Now we have the signed less. Let's go. Unsigned. Szak wpierdzie. Wpierdzie. Nie szak wpierdzie. White instructions. No, I'm gonna cut this. No, I'm not.